In this video, we will continue our exploration of C's preprocessor by delving further into macro expansion. In particular, we'll look at macro expansion in the context of function-like macros. But before we start, 2 words of caution. First, many of the features that we are demonstrating are system-specific, so they may not work the same on your computer. Secondly, for this and other reasons, using function-like macros is rarely, if ever, a good idea. You will encounter them in existing code, but I do not recommend using them in your own code. More on this in the video. Let's start with an example. These macros are from an operating system simulator. The first 6 macros define a series of bit flags for the virtual memory system. In the last video, we said that it's a good habit to wrap all macro values in parentheses, but in many real-world examples, like this one, you'll find that macros with simple values, like integers, don't do so. The last line is an example of a function-like macro. The macro defines an operation called set that operates on 2 parameters. The bit at the position identified by the parameter flag is set in the variable var. Here are 2 examples of the macros in use. Let's look at how they are expanded. The set macro is used as if it were a function. It receives arguments, and the user added a terminating semicolon so that the operation runs on its own as a statement. Every instance of the 2 parameters is replaced by the arguments in the corresponding positions. Var becomes page flag, and flag becomes the number 3. It's 3 instead of page user because page user is also a macro. The second expansion of set is similar, but with a different second argument provided. The results make sense. When we set the page user flag, which is bit 3, we see that the resulting value is 2 to the power of 3, or 8. And setting page dirty, which is bit 4, results in 2 to the power of 4. This OS example is a bit more complex because various macros interact. Let's compile and run it. In this example, a warning message tells us that page user is set. This is implemented using nested macros. The isSet macro is used to supply a condition to the warn macro. The warn macro checks the condition and emits the condition as a warning message if the condition evaluates to true. The macro introduces some new features, so let's take it apart. The core of the warn macro is wrapped in a do while. Since the condition in the while is false, and will always be false, the body will execute exactly once. So why use the do while at all? It has 2 purposes. First, it enforces a requirement that the warn macro be used as a statement. Here, let me show you. If the semicolon is omitted, suppose for example that we were to use the macro in a place where a semicolon doesn't make sense, then you'll get an error during compilation. The second purpose for using a do-while structure in a macro doesn't apply here. It allows macros to include multiple statements, and some of those statements can be local variables. They'll exist within the loop, but not outside. If that makes you cringe, I'm glad, but you may see it in systems or legacy code. The last interesting piece of the warn macro is this extra pound sign. This is the stringification operator. This operator preserves the argument as a string. In this case, the argument is a macro application, which is kept from expanding. It will also preserve C code as a string. As you can see, function-like macros can be very useful. So why did I say that using function-like macros was rarely a good idea? Take a look at this macro. It looks simple, but it's the canonical example for why macros are difficult to use correctly. As you can see, the macro greater expands to an expression that evaluates to the greater of its two arguments. Let's say that we want to take the greater of x or y, but only after incrementing y. Here's one way to do it. Update y, then check which is greater in separate steps. And here is another where y is updated within the expression, but we get a different result. Why? Let's look at what the preprocessor generates from this code for the body of the printf statement. The programmer probably intended that the argument be evaluated first, as it would for a function, but instead, ++y gets executed twice because it is simply copied into the macro. So the issue is that the macro looks like a function. Since it looks like a function, we expect it to act like one. Here's another example. Do you see the problem with set? Let's use set as an expression instead of a statement. In this case, it will work. An assignment statement evaluates to the value that was assigned, so we'll print what we expect. So since that worked, someone less careful than you might decide to nest the set calls to try to set both bits. Fortunately, when that fails, we get a relatively comprehensible error message. Let's look at what the preprocessor generates for our program. We see that the nested set calls expand to this mess. First, the inner use of the set macro is expanded to this expression. And then that expression is used as the second parameter, var, in the expansion of the outer set call. The problem is that C won't allow us to assign to an expression. So we are warned that we can't assign to an expression. If we had wrapped the code in a do-while, we'd get a slightly cleaner message. But that doesn't fix all of the problems. You may have wondered why all our examples include so many parentheses. The issue is order of operations. A user can pass in a macro, or any arbitrary expression. The parentheses around the arguments force them to be evaluated first, as would occur if a function were being called. Without these parentheses, we don't know if the arguments will evaluate first or after part of the internals of the macro evaluate. Similarly, the parentheses around the macro force the entire macro to be evaluated, regardless of where the macro is placed. This is another attempt to make macros act like functions, which evaluate fully before returning a value. So by convention, we always use parentheses around the arguments as well as around the entire macro. But if we have so many conventions that are trying to make macros look like functions, why not just use functions? One argument in favor of macros is that they are faster, since they don't require a function call. But inlining a function removes that argument. The other argument is that macros are type neutral. Our greater macro works on any type. But that flexibility is also a weakness. By operating outside of the type framework, misapplications of greater onto a double and an int, for example, occur silently without the assistance of the compiler. Another weakness of macros is that most compilers do not include macros in their debugging information, which can make it harder to debug problems with macros. Almost anything that can be done with defines can be done within the C system. So my recommendation is that you only use function macros in rare cases. However, lots of legacy code uses macros, so it's useful to be able to read them.